Thank you very much. I do have to tell you that Bradley holds a special place for me because I used to come watch the Bradley basketball games in the old Robertson Fieldhouse with my dad, and we used to watch a guy named Roger Fegley. That's me down here. We used to watch Roger Fegley play there, and that was really a thrill. He used to play against a guy from Indiana State. It was Larry, that was it. Larry Bird. Yeah. I wonder whatever happened to that guy. I did play a little basketball on my own with Todd Barrowman. We played a little ball at Washington Grade School, go Wildcats. I ran my first steamboat 4-miler in 1976 and graduated Richwoods High School in 1984. Anyone else graduate high school in the 80s? Let's see a show of hands. 80s? Okay. How about you have kids who graduated high school in the 80s? How about grandkids who graduated high school in the 80s? You'd have to be really old for that one. Who was not born yet in the 1980s? Okay. Good. Good. It's important to know your audience. So, last year I had the opportunity to work with NASA's Operation IceBridge in Greenland through a program called PolarTREC, which, as you just heard, pairs polar researchers with educators. It's a fantastic program. If you have someone who teaches science, tell them to apply for the program. But none of this would have been possible without the support of taxpayer-funded organizations, your tax dollars, places like NASA, PolarTREC, the Arctic Research Consortium, and the National Science Foundation, all paid for this experience for me and to bring it to you today. So for this talk, we're going to feature the science and adventure of Operation IceBridge, why science, technology, engineering, and math, known as STEM fields, are important for all students, especially those not born in the 80s, and why studying climate change is important. Let's start with a bit of the adventure. Operation IceBridge is a 6-year airborne science mission to gather data on polar ice in unprecedented detail that will allow future scientists to better understand the complex climate of the Earth. It's no exaggeration to say that teachers, those working in support of teachers, parents, grandparents, you are literally training the next generation of scientists for whom this data will be critical. Operation IceBridge combines cutting-edge science and engineering with this amazing adventure to the most remote parts of the globe in a mix that for a nerdy guy like me was simply astounding. Gotta line it up with the runway. So where is Greenland? Well, this video might give you a little better perspective, starting in Libertyville, Illinois, where I teach. And we're going to go to Greenland, which makes tiny Denmark the 12th largest country in the world by area. Now, Greenland is 800,000 square miles. That's about the size of Mexico, but it has the population half that of Peoria, about 57,000 folks call Greenland home. 80% of it is covered by ice, as you can see in that image. It's the second largest ice sheet on the planet after Antarctica. Okay, you got the first question right. This ice sheet is what remains after the last glaciation that covered vast expanses of the Earth, including much of North America 12,000 years ago, and it's the ice that Operation IceBridge is interested in. We were based out of Kangerlussuaq, a town of 500 at the head of one of the world's longest fjords. It was built in 1942 when the Allies were afraid that Germany would invade North America. They didn't. The ice sheet comes within 10 miles of Kangerlussuaq. It's visible just here out of the picture. There's actually a road that goes all the way there, and you'll see me on that ice sheet later. So Greenland is mostly ice, and Iceland is mostly green, as you might know, in what may be the the world's first case of false advertising. Now, it had been settled for 4,500 years by people who literally walked there. It was first settled by the Norse cultures in the 10th century. So I know the Italians love their Christopher Columbus, but the Scandinavians beat him there by about 500 years. So skål to all you Scandinavians. Greenland became important during World War II. How many people were alive during World War II? I know we have at least one veteran of World War II. Ken Jones, where are you? Back in the very back corner, Ken Jones. So it was important, especially to Germany, who needed better weather forecasting. So they planted some weather stations in Greenland on the eastern coast, and one in Canada. Not very many people know that. And the U.S. was the protectorate because Denmark was occupied by Germany. So we went there, blew up a few weather bases, and then built a few air bases. We built the largest one, known as Bluey West 8, back in the World War II days, and then became known as Sonderstrom Airfield, and now known as Kangerlussuaq. It's used now as their international airport. During the Cold War, the U.S. built a base at Thule, you might have heard of, part of the DEW line. That is still an operational U.S. air base. The one in Kangerlussuaq is not. It's just their international airport now. An interesting side note here is that to get to Greenland in the spring, when I went there, or the winter, there's only 5 international flights per week that get to Greenland. And they all originate from Copenhagen, Denmark, right there. So to get to Greenland, I flew from Chicago, crossing over the southern end of Greenland, practically right where I needed to go. I asked the flight attendant for a parachute. She did not find that funny. You land in Copenhagen, then you wake up the next morning, you fly 2/3 of the way back across the Atlantic to get to Greenland. You fly about 6,000 miles to cover what could be a little 2,000-mile trip right there. So what is Operation IceBridge? Well, they have a Facebook page, and we should all like it. Doesn't everyone have a Facebook page? And they have a great website, but maybe you're thinking, why ice? Well, here's why. It's easy to understand why we study earthquakes. And those earthquakes don't have to happen in the United States. We study earthquakes because there's an immediate and obvious impact on all of us, whether it's in terms of property damage or infrastructure, whether it's in terms of economics or loss of life. And plus, there's a science to understanding earthquakes, and there's a value in predicting when earthquakes could happen or where they could happen. That's pretty obvious. Well, climate change and melting ice might not be as immediate, but it's hopefully as obvious why we would study that, because there could be a huge impact on infrastructure, property damage, economics, besides the fact that it's science. And the more we learn about the science, the better we can predict what will happen in the future. And that's what Operation IceBridge does. They collect data that allows scientists to predict and understand what's going on. That's the key. They started with ICESat-1 in 2003. It flew from 2003 to 2010, and it mapped polar ice. It measured all kinds of parameters about polar ice. It stopped working in 2010. They knew that, but they did not have another satellite ready to go, and they still haven't launched it. It's going to launch in 2016, so there's this 6-year gap, hence Operation IceBridge, to fill the gap from 2010 to 2016. They didn't want to lose those years of data. And while the satellites might give you kind of this big picture, wide-angle view, from an airplane, you can get the HD view of what's going on in the ice. And they do it from sometimes a DC-8, but mainly a P-3 Orion. These planes were built for the Navy back in the Cold War days to hunt submarines. You can see this thing on the back called a magnetic anomaly detector, or MAD boom. And that's where they put the magnetometer, which would help them detect the submarines in the oceans. Well, now NASA has repurposed one of these old aircraft, and it flies under the NASA logo here. A P3 is 116 feet long with a 100-foot wingspan, so it's about the size of a 737. Probably been on one of those. With 4 big turboprop engines, it has plenty of power to get all the science gear that's inside off the ground and to climb up out of these glacial valleys, which you've seen one video, and we'll see a couple more here. As a sub-hunter, it was designed to fly low and slow. And when I say low, I mean 1,500 feet or less at 250 miles an hour. And that's what they want, to gather data on ice, to get down close to the ice and image that ice and measure the parameters about the ice that they need. Most of the missions were about 2,000 miles and lasted 6 to 8 hours. And what about that science gear? Well, the inside doesn't look anything like your 737. The inside is crammed full of science gear. What kind of science gear? Here's another view looking forward from about the middle of the plane. 2 laser altimeters, one wide scan, one narrow scan. 4 different radars that penetrate the snow and ice to different depths, including one that can go all the way to bedrock. 2 digital mapping systems. These are digital camera systems that take pictures of everything they fly over. They can even generate stereoscopic images from these. A magnetometer, back in that NAD boom, to measure changes in the Earth's magnetic field, gives them clues as to what's under the ice. A gravimeter, which measures changes in the Earth's gravitational field, again, giving them clues as to what's under the ice and how much ice there is. And a spectrometer, which measures the reflectivity of the surface. The more reflective the surface, it's probably going to take longer to melt that ice. The less reflective the surface, probably going to melt faster. So simple things like that. And, this probably won't surprise you, it's designed, built, and operated by some of the brightest people I've ever met. And I have worked in places where we were doing rocket science. And these people are incredibly bright, incredibly driven, incredibly talented. That's no surprise. This walkthrough will give you another idea of how it all fits inside. It's very much a science platform as much as it is an aircraft. And as we get to the back, I'll just point out, there's a galley and a bathroom on the plane. 8 hours is a long time to go. And while this plane was built in 1967, although parts of it have been replaced, it's also been upgraded with some of the most sophisticated avionics on the planet. The pilots literally fly a video game console, you'll see that on the yoke right here, to keep the plane on track. And we'll get to that as well in a little bit. And it's all about data. They want data. They can't get enough data. In this room right now, there are 68 processors running to process the data and copy the data that they gather every day. So on cold days, if you need to warm up, this was where you went. There's 68 computers running in there. They gather more than 2 terabytes of data per day. To put that in perspective, the Library of Congress, the printed material for the Library of Congress occupies a space of about 10 terabytes. Operation IceBridge gathers that much data in less than 5 days. And let's review a little math for you here. Put on your thinking caps. A photo, a fairly high-res photo, is about a megabyte. Certainly a lot are bigger now, but that's a good-sized photo. There's 1,000 megabytes in a gigabyte and 1,000 gigabytes in a terabyte. That means there are 1 million megabytes in a terabyte, and Operation IceBridge is sucking up more than 2 million megabytes every 6 to 8 hours that they fly. That's a lot of data. And that was a lot of math, so let's go to some more adventure. Let's take a break. Here's that mission to the Penny Ice Cap, great name, on Baffin Island over here. And so here we were in Kangerlussuaq, and we flew over here and mapped the ice over here and flew back. Boy, it's pretty interesting to me why we would be interested in such a tiny little ice cap over here. They call it an ice cap, not even an ice sheet. When the second largest ice sheet in the world is right here in their backyard. I wonder why they would bother with that one. Well, hold that thought. Here's a map of all the flights flown by IceBridge in a typical spring. In our fall, spring in the southern hemisphere again, they go to Antarctica and do the same kind of thing. But you can see that they pick up a little ice cap here, and they map Greenland quite extensively. And they're also interested in sea ice. A lot of people are interested in sea ice. There's oil and gas and shipping to be done up there if it keeps melting like it is. Here's a close-up of another mission we did. These red squiggles on here, these are the Glacier Runs. That's the exciting part of the videos, when the planes literally feel like the wingtips are going to hit the sides of the fjord or the sides of the valley. And they're very exciting. They can also be the most turbulent parts. Down here, over the Jakobshavn Glacier, is what they call mowing the lawn. They're just trying to gather a lot of data over a large area and see what's going on. And the Jakobshavn, you might think of it as the Amazon of Greenlandic glaciers. It's that important to how the whole thing behaves. How about these long crossing tracks? What do you think those long, straight tracks might be for? Why would you fly that? Satellite tracks. Either they're picking up data that was already gathered, like maybe ISAT-1 flew over these tracks a few times, and now we're going to fly over them again in 2013 and see how the ice is changing. Or ISAT-2 is going to fly that track, and we're going to fly it now in 2013 to get some preliminary data. So anytime you see those long tracks, those are the satellite tracks that they're flying. They're trying to bridge that gap. Here's a little closer image on a different kind of map. So you can see that mowing the lawn pattern, and they're looking at kind of the whole area around that glacier, and then getting in close and getting some HD kind of resolution in close here. And this again is the Jakobshavn Glacier. It's a huge glacier. The whole island it's a big dome in the middle, and all the ice flows out through these what are called outlet glaciers. And 90-something% of them are marine terminating, meaning they end in the ocean. And so they're flowing this way. And you can't think of ice as being a solid substance when you're studying glaciers. It flows like pancake batter or Play-Doh. So if you can imagine that flowing under pressure, that's how you have to imagine glacial ice flowing. Again, here's just a quick shot of some of those glacier runs, the exciting parts of the flying. And the pilots have big grins on their faces doing that kind of flying. Now, in order to gather meaningful longitudinal data, you have to fly the same paths year after year after year. You have to fly exactly under that satellite track. And so they do that with GPS. They know exactly what paths they've flown in previous years. That's this path. And now, this year, you got to put the plane over the same path. Turns out, NASA hires some pretty good pilots. 95% of the time, they're within 100 feet of the center line. That's plus or minus 50 feet. And the scan width is only 750 feet wide. So they are on the center line 95% of the time. And that gives them that longitudinal data. We need to know how this is changing. We can't just go up there and gather it 1 year and make any kind of prediction. You have to take it year after year. Let's take a look at a little detail here of how they do that. Sorry, small technical difficulty. Let's get that plane in here again. So let's start with sea ice. And the green represents the laser altimeter. And it's a visible green laser, not unlike the one I have in my hands, just a little more powerful. And it'll bounce off the top surface, whatever the top surface is, snow, ice, water, anything, it'll bounce off the top surface. The radars can penetrate different depths, and they have one radar that penetrates through the snow and reflects off the ice, and they have others that'll go right through the ice. No radar penetrates water. It's impervious to radar. But by measuring where the top surface is, what the snow load is, and where the bottom is, where the sea level is, and then knowing the density of ice and the density of seawater, you can perform a fairly straightforward calculation and calculate exactly how much sea ice there is. If we move over the ice sheets, they have one of the 4 radars will penetrate all the way to bedrock through kilometers of ice. It's a very powerful radar. And again, knowing where the top surface is and knowing where the bottom surface is, you can get a very accurate measurement of how much ice is there. And if you do this year after year after year, you can tell exactly how that ice is changing. From the data, they can generate some very simple elevation profiles. They can color code the elevation profiles, that's the code over here, and they can lay those over the digital images that they're taking constantly, and so you get an actual view of what the ice looked like at that particular time. All right, here's your next quiz. Where's sea level in the image? Where's the ocean? All right, you're looking for blue, so that's this whole area here. This is the fjord. So this is a marine terminating glacier. Can you see where the head wall or the calving front of that glacier is? Right here on this squiggly line here, where the elevation starts to change. You're going uphill. And those are the paths that the plane would fly to map that ice. And they'll do that year after year. When I talk about HD vision, I mean they can get really incredible images. Just from the laser altimeter, you can see the crevasses in the glacier. Right? And again, it's color-coded, so we're going uphill as we go this way. This is actually 2 images of the same glacier laid next to each other, the Jakobshavn, that Amazon of Greenlandic glaciers. We flew over it on April 4th, and it looked like this. 6 days later, the calving front was 250 meters upriver. Now, some of that's normal. I mean, glaciers are constantly flowing out to the sea and breaking, calving off, sending icebergs down the fjord to sink the Titanic. But they can see that in high-resolution detail, and that's pretty amazing. The ice-penetrating radars can go all the way down to bedrock, and this is very important for glaciologists like Michael Studinger, the lead scientist who's a glaciologist. He wants to know what's under the ice so I can model how that ice is going to slide out to the ocean. And that's what we're looking at here. This is the actual bedrock, and the ice is so heavy it's depressed the canyon 1,400 meters below sea level. There's a trench from that weight of all that ice above. And again, just let me remind you here, the interior is very high, 10,000 feet in the highest places in Greenland. And it all flows out all around the island, or outlet glaciers, so it's just squeezing out through all those gaps. This is a pretty incredible image. It's actually a composite of 3 different images. Here's the digital mapping image. That's just a digital photograph, and you can see these crevasses in the glacier. Here's the calving front. In the laser altimeter profile, here's the calving front, and look at these. There are the crevasses again. Using all their data and combining all their sensors, you can get these incredible 3D models, inside-outside view, all the way down to bedrock of what that glacier actually looks like. You can see the icebergs floating in the fjord. Of course, these are false color images, coded by elevation again, because everyone knows what color a glacier is, right? I mean, that's obvious, isn't it?
of something just to get him through to Christmas and into the new year. And I am just another weary Christopher Columbus. I'm sailing this blue ocean with my head held high. And all these currents are leading me astray, taking me away from the places that I'm seeking. And all these currents are leading me astray, cause I am just a drop amongst the waves we're making. Oh, I am just a drop amongst the waves we're making. Every now and then I stop and think about the future, and I listen very closely for a slice of reason. It's hidden in my headphones, do I turn them up loud enough? I can hear all the ugliness and beauty inside. And all those lyrics were lying anyway. The singing ships were safely moored in front of me, babe. And all those lyrics were lying anyway. The sea lights faded when the morning came. Oh, and I don't know where you are from, but my God, I would like to know. And I don't know where you are from, but my God, I would like to know. Capillaries is flowing with a vigor that I haven't felt for years now, and I'm enjoying it again. Hunting oxygen that dances through the streets unprotected. I am part of every moment, I am every fingerprint. And all those voices were keeping me awake, telling me that I can never be what I can be. And all those voices were keeping me away, but I'm learning not to listen to anything they say. Oh, and I don't know where you are from, but my God, I would like to know. And I don't know where you are from, but my God, I would like to know. And I don't know where you are from, but my God, I would like to know. And I don't know where you are from, but my God, I would like to know.
Yeah, if you're on social media, friend Alan Pope, he posts some incredible kind of imagery. It's neat. I got to meet him through this NASA program. I should have said that was not my video before it started. So here's one of the questions that I was supposed to answer. Why are science, technology, engineering, and math vital for all of our students? The STEM fields, as we call them in education. It's because technology is here to stay. But I had students say, well, I'm going to be a doctor. Do I really need all this physics? And I said, well, have you ever heard of advanced imaging techniques or robotic surgery? Yeah, I think you're going to need a little physics. Or I'm going into business. Do I really need this technology stuff? Well, what are the biggest businesses in the world? Those that deal with technology. And even the businesses that don't deal with technology directly are using technology in ways that we couldn't have imagined 10 years ago. And 20 years from now, there's going to be jobs that we can't imagine today. So technology is with us to stay. So even if our students are not going to major in science, technology, engineering, and math per se, they better keep one foot firmly planted in that world. So for 2 full days, I spent not flying, and I was on the ground connecting with students around the country, grade school, high school students, wherever I could find students to connect to. And they are infinitely curious. That's me on the big screen. And they'll come right up, as long as the teacher will let them go, they'll come right up and keep asking questions and asking questions. It's amazing. As a high school teacher, a lot of my high school students are a little jaded. and as a high school teacher, I'm not always in tune with the energy and excitement that exists in a 3rd grade classroom, but you point the camera at the 3rd graders and they go crazy. And this is me down here wondering what the hell I'm going to do with them now. So while I was there, I journaled every day, took hundreds of pictures, and posted 42 videos online. They're still up there. And my classes got a chance to chat through a text system in the Global Star satellites. They could actually be in the classroom in Libertyville, Illinois, bounce a signal off a satellite down to the plane while it's flying, and chat with us in the plane. That system is now available to any classroom of any age, anywhere in the world. That's one of the pushes that NASA has made. So that's an amazing thing that your classroom teachers could do in whatever community you're living in. So while 99% of the trip was work, there was still 1% left to make friends and go for a run. Go up and hike on that glacier. Here I am standing on a couple hundred feet of 40,000-year-old ice. And sample the local cuisine. Besides the stuff you probably recognize, on this plate are also seal, muskox, reindeer, caribou, and whale. It was all excellent, except for the whale. Don't eat whale. And then to the last part, is Greenland melting? Well, the short answer is yes, it is melting. Since 2000, it's been losing, on average, 300 gigatons of ice per year. And that's a metric ton, so that's a little bit bigger than a regular ton. And a giga, again, is a billion, so 300 billion metric tons per year, until about 2 years ago when it started losing over 500 gigatons of ice per year. Now, there's a lot of gigatons up there. It's not like it's going to go away tomorrow. But a gigaton is about a cubic kilometer, so it's losing 300 to 500 cubic kilometers of ice per year. So it's definitely melting. There's no arguing that point. And why do we care about climate change anyway? I don't know. Maybe we don't, because actuarially speaking, very few of us in this room are going to need to worry about it. I mean, this is a problem for the future. But what is the future going to need from us? Data. And that's what they're doing right now. Let's remember that weather is short-term change. The weather was nice today. Climate are long-term changes. We're talking centuries and millennia of change. So let's look at climate and see if you can spot the trends as well as anyone with a pair of eyes can. We're going to go back to 1884 and look at average global temperatures from then to the present day. So we're getting a little warmer. Now the dark red represents about a 2 degrees Celsius temperature change. Call that 4 degrees Fahrenheit. And you can see this as well as any other climate scientist. Where is it getting warmer faster? The Arctic. That's why IceBridge is spending a lot of time up here in the Arctic. They're interested in this. Why is this happening? We can start to answer that question in a little while. But it's a couple of degrees, right? How big is a couple of degrees? Well, here's a nice little cartoon. For our lives, and really for many of the last few thousand years, we've been in a really sweet spot in terms of climate. We've put 7 billion people on the planet. We're growing more food than we can eat. It's kind of a sweet spot, though, because 20,000 years ago, and this is a temperature change of about 8 degrees Fahrenheit down to here, where I live in southern Wisconsin, I was under a couple thousand feet of ice. We go up 8 degrees, and we're heading that direction, as anyone can see from that little clip. What's that going to look like in my neighborhood? Are we going to be able to grow food there or not? Are we going to be able to milk cows for cheese? I'm from Wisconsin. Or not? We know what happens if we go up 16 degrees. That's a pretty incredible period of time. That's the Cretaceous hothouse period. We had ginormous plants. There was virtually no ice on the planet. Sea levels were about 700 feet higher than they are today. So you're going to be buying beachfront property in Madison, Wisconsin. Maybe that's okay. All right, so let's zoom in on Greenland and take a look what's been happening there since 2000. We've been gathering data with IceSat-1, and we've crisscrossed the island. Now we've got IceBridge flying, and we are mapping everything we can map as fast as we can. Look at the data. I mean, we're gathering a ton of data. And what's it showing in kind of the big picture from 2000? I'm going to stop this if I can. Right about. Oops. Let me just go back. 1. right there. So what's happening? You can read the color code as well as any glacial scientist. So yellow represents an actual increase in the amount of ice. Sure, there's parts of the island that are actually getting more ice and snow, but that's a positive 4-meter increase. There's also some places where there's a negative 36-meter decrease. That's more than 100 feet elevation of ice. And where is it happening? These outlet glaciers. In a sense, right now, we're uncorking the bottle. And what's going to happen after we uncork the bottle? We don't know. How are we going to know? Gather data. Keep gathering data, and that'll allow future scientists to make better predictions. We can make all the predictions we want today, but they're going to be more accurate in a decade with more data. And temperature change might not be the most immediate concern, right? I remember my grandmother, my mom's mom, sitting on the back porch when it was 95 degrees asking for a sweater. So maybe warmer temperatures aren't necessarily a bad thing for some of us. What's probably the most immediate concern for not only us in the United States, but around the world, because we live on the oceans, is sea level rise. Every piece of ice that melts makes the oceans go up a little bit. We've got plenty of data going back further than this graph shows. But what's it mean? Where is it going from here if this trend continues? Well, on the low end, it might not do much at all. On the high end, by the end of the century, that's just 86 years in the future, it could be up 2 meters. I mean, if you're a betting person, you're going to bet, you're going to put your chip somewhere in the middle, right? But 1 meter, 3 feet, is that really a big deal? I mean, the tides are bigger than that. No, remember, this is on top of the tides. This is base sea level. So if you live on the East Coast, this is what's going to flood with a 1 meter increase in sea level. That's just 1 meter increase. You want a vacation in Florida? Better come back from the beach a little bit, right? And remember, you have a hurricane with a 15-foot storm surge, that's catastrophic. Now add 3 feet onto it, making an 18-foot storm surge, that's cataclysmic. And that's 86 years. If, you're right, I mean, how do we know? Data. It's the only way we're going to be able to predict the future, more data. And Arctic sea ice is important. That's why they fly missions over the Arctic basin. This is showing you what's happening to the minimum Arctic sea ice through 2012. We started in '79 with a minimum of about 6 million square kilometers. We're running about half that these last few years. Here's why it could be very important. Sunlight reflects off ice and snow. About 90% of the sunlight that hits it reflects off of it. Water absorbs about 90%. So that might explain why that Arctic was getting so much warmer, so much faster than the Antarctic. The Antarctic is ice, and it's ice all the way down. We got kilometers of ice there. But we've only got meters of ice up here. And when they melt, what's underneath is something that absorbs all that energy very easily. So that's called a positive feedback mechanism. When more melting leads to more melting, which leads to more melting. And going back to the penny ice cap, why were we interested in the penny ice cap? Because if you look at this first column of volume, these small glaciers and ice caps make up virtually none of the ice on the planet. Greenland only makes up 10% of the ice. I mean, most of it's trapped down there in Antarctica. 85% of all the ice on the planet is down there. But what's contributing to sea level rise right now? That's the red graph. 60% of the sea level rise is coming from those small ice caps and glaciers. This represents in real numbers about 2 millimeters. That's about that much. But that's 2 millimeters every year. Greenland is contributing about 1 millimeter per year to sea level rise. But if we can understand this, maybe that gives us a better idea of this, and that could give us a better idea of what could happen over here. So why do we care about Greenland melting and climate change anyway? Because like I said, actuarially speaking, it's not going to be a problem for any of us here, except, well, who's the youngest person here? Raise your hand if you're under 40. 40 or less. 20 or less. Okay, so it's going to be a problem for those guys. And certainly their children, right? That's who we're gathering this data for. As a physics teacher, as an engineer, I was thrilled to be a part of NASA for a month, to go on this amazing adventure with brilliant people and do some really high-tech stuff. But as a father of 2 young children, I was really proud to be part of a team that was not gathering data for themselves. They're gathering data for the future, so that someday one of these kids can take all those terabytes of data from ISAT-1 and IceBridge and ISAT-2, plug them into their climate model, and come up with something that's going to help them. It's going to give them some accurate predictions. And it may give them insight into the world they live in, and it may give them insight into how to change the world that they live in or fix the problems that they see. And that kid, somewhere in the future, is going to look back and thank all of us for doing it. That's why we want to do it now. All right, so let's look at one last video to highlight the adventure that is science.